Welcome to Curious Minds. Today we're rolling across Mars, how the entire rover idea was born, how it survived, well, brutal failures, frankly, and how it's currently reshaping the search for life.
Yeah, it's really a journey of persistent generational engineering. Started small, scaled up to these nuclear-powered flagships we see now.
It's an incredible technological progression. I mean, if you chart the whole arc.
Right. We've moved from, tiny solar scouts landing in airbags, basically a beach ball bouncing down, all
Yeah.
the way up to complex rocket cranes, gently lowering, a car-sized laboratory.
And now with a helicopter sidekick, too.
And a helicopter sidekick.
Oh.
Exactly. End-to-end evolution.
And that technological leap wasn't just, nice to have, it was mandatory. Our mission today is to understand that exact progression, how technology lets us explore this hostile, distant world with unprecedented machine independence.
And that independence is absolutely fundamental because Mars, the environment itself, is actively working against our hardware.
And against our ability to control it in real time.
Right.
That's the big one.
That's the killer, the communication gap.
Let's talk about that. I mean, the moon landing felt almost instant in comparison. Mars is just different. How bad is that control latency?
It creates an insurmountable delay, really.
Yeah.
For Apollo, the moon signal delay light speed was just over 1 second. We could guide them,
Yeah.
react.
Okay.
There's so much further. During, say, the critical landing phase, EDL, entry, descent, landing, that one-way signal delay is 11 minutes.
11 minutes one way.
Yeah.
So if mission control sends a command, 11 minutes to arrive.
Right. And if the rover sees a problem like a cliff edge during landing,
We won't know for another 11 minutes.
exactly, meaning the event itself happened, 11 minutes before we even get the message.
So a 22-minute round trip minimum.
Precisely. And that dictates mandatory autonomy.
Yeah.
The rover's computers have to handle the whole landing, navigation, survival sequence, no human intervention possible in real time.
Wow.
And then you have the physical threats on top of that. The thin atmosphere, it really complicates landing.
Yeah.
Massive dust storms. They can just block out the sun, kill solar panels. We saw that.
Right. With opportunity.
And the temperature swings. Extreme.
Yeah.
Highs, maybe 27 Celsius, okay? But lows down to minus 133 Celsius at night.
Minus 133 C. That'll destroy components.
Oh, yeah. Makes things brittle, electronics fail. It's brutal.
Which makes the timing of the whole mission critical, doesn't it? Not just on the surface, but getting there.
Yeah.
You have to wait for Earth and Mars to line up just right. I always picture it like planets on a racing track.
That's a perfect analogy, actually. Because of those orbital alignments, the launch windows only open up roughly every 26 months.
So miss it, and you wait over 2 years.
Yep. And then the cruise itself takes 7 months. So every mission needs this huge amount of pre-planning, generational foresight, really.
And the big scientific payoff for all that difficulty? Mobility. Why are rovers so much better than just landing something in one spot, like Viking did back in '76?
Mobility just fundamentally changes the science you can do. A fixed lander? Great science, but only at one spot. A rover turns that one landing site into potentially hundreds of science sites. You can follow geology, chase clues across the landscape, ancient riverbeds, mineral veins, whatever looks interesting.
And this dream of a mobile lab, it actually started pretty early, didn't it? Even before Viking?
It did. Both the US and the Soviets were studying mobile concepts back in the 1960s.
Really?
Yeah, the Soviet Union developed this little thing called Pro-PM, a micro rover, only about 4.5 kilograms. Really odd design. Used rotating skis instead of wheels.
Skis. Wow.
Yeah, little skis and feel rods for obstacles. It was attached to the Mars 3 lander in 1971, but sadly the lander failed just 110 seconds after it touched down.
Ah, so the rover probably never even got deployed.
Likely never deployed, so that mobile dream, it had to wait.
Until the undisputed champion arrived, the one that proved it could be done, NASA's Sojourner.
1997. Mars Pathfinder mission delivered Sojourner,
Yeah.
our first successful rover. And it was really a tech demo. Tiny, solar-powered, about 25 pounds.
So small.
Its main job was proving the tech, especially that innovative airbag landing system, just bouncing down safely.
Right, the beach ball landing.
Exactly. And proving basic driving, obstacle avoidance. Could it work? Yes.
And what was the key takeaway from Sojourner? The thing that really changed future planning?
I think it was the sheer outperformance. It was designed for maybe a week.
A week.
Yeah. It lasted 83 days, traveled about 100 meters, and crucially, it did real science. In situ chemistry on rocks like, the famous Barnacle Bill and Yogi.
Ah, I remember those names.
It just proved that a remote vehicle, even a tiny one, could operate, survive, and deliver actual science. That made the case for investing much more.
Okay, so that success paved the way for the next big step. The workhorse geologists, Spirit and Opportunity, launched in 2004, a major step up in scale, right?
But absolutely. Significantly larger, about 180 kilograms each. Still solar-powered, though, and still using those airbag landings.
But designed for much longer.
Nominally, 90 sols, 90 Martian days. But their longevity just became legendary. Spirit lasted over 6 years. Opportunity. Nearly 15 years. Incredible.
15 years. And they were the ones that truly cemented the idea of ancient water on Mars, weren't they? Finding those layered rocks, the hematite blueberries.
Absolutely. Those blueberries hematite concretions, they pretty much only form in water. That, plus the sedimentary layers, confirmed Mars was once wet, warmer, potentially habitable. Huge breakthrough.
But you mentioned they were solar-powered.
Right, and that was ultimately their Achilles heel.
Which brings us to, well, a sad moment, but a crucial one for design. Opportunity's end. How did losing Opportunity shape the next generation?
Opportunity was finally overcome by a massive global dust storm in 2018. The dust just blotted out the sun, solar brightness dropped by like 96%.
Wow.
Its power levels just plummeted below the minimum needed to keep warm and survive. That failure made it crystal clear. If you want a long-term, all-weather rolling lab on Mars, you cannot rely solely on the sun.
Enter Curiosity. The Mars Science Laboratory landed in 2012. Let's do that quick rover family portrait. Sojourner was maybe suitcase-sized.
Yes.
Spirit and Opportunity, maybe like riding lawnmowers.
Good analogy, yeah.
Curiosity was the first car-sized rolling lab, 5 times heavier than Spirit or Opportunity.
That massive increase in size and weight was driven by the power source shift.
Yeah.
To the RTG, the radioisotope thermoelectric generator.
Nuclear power, basically.
Essentially, yeah. Uses the heat from decaying plutonium-238, gives about 110 watts of electricity initially, but consistently, day, night, dust storm, doesn't matter.
Solve the dust problem and give it that all-weather longevity.
Exactly.
But landing something that big and heavy, you couldn't use airbags anymore. That's where we get the famous 7 minutes of terror. Can you walk us through that? It sounds insane.
It is absolutely insane engineering, and it's all autonomous, remember. The whole sequence takes the spacecraft from about 13,000 miles per hour at the top of the atmosphere down to a dead hover in 7 minutes flat. So first, massive heat shield takes the brunt. Then a huge supersonic parachute deploys, slows it down dramatically. Heat shield jettisons. And then the descent stage, the sky crane kicks in.
The sky crane.
Yeah, this rocket-powered jetpack thing. Fires 8 retro rockets to slow down even more, eventually bringing the whole package to a hover about 20 feet above the surface.
Hovering a car-sized rover on rockets. And then the dramatic finale.
Right, to avoid blasting the landing site with rocket exhaust, the sky crane lowers Curiosity down on a 21-foot bridle, like a spider on a thread.
Wow.
Once the rover's wheels touch down and it signals it's safe, the sky crane cuts the cables and flies away to crash deliberately a safe distance away.
Just mind-blowing. A completely unique, brilliant way to land something heavy with pinpoint precision.
It really is.
Great.
And that successful system became the foundation for the current generation, which brings us to Perseverance, landed in 2021.
Right. And Perseverance looks almost like Curiosity's twin, uses the same sky crane, same RTG power.
Yeah.
But the big leap is inside, isn't it? The intelligence.
That's the key difference. It uses maybe 85% heritage hardware from Curiosity, but the autonomy. It's a staggering leap. The new Thinking While Driving software is revolutionary.
How so?
It allows Perseverance to map hazards in 3D, plan optimal routes, and just drive much, much faster and more continuously than operators back on Earth ever could by commanding step by step.
So it's making its own decisions on the fly.
Largely, yes. It set new planetary driving records. It autonomously planned something like 94.8% of its routes on a recent stretch, drove over 5 kilometers in just 31 sols. Its speed isn't limited by computation anymore. It's limited by how fast the wheels can physically turn.
So after solving the distance problem partly with hardware, the RTG, they finally tackled the rest of the distance problem with intelligence. Smart autonomy.
Exactly. Lets us really traverse the surface efficiently.
But Perseverance is also doing groundwork for humans, right? Experiments like MOXIE.
That's the forward-looking piece. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. It's designed to take Martian air, which is mostly carbon dioxide, and convert it into pure oxygen. Produces about 20 grams an hour. It's a vital proof of concept. Shows we can potentially generate breathing air for astronauts.
And rocket fuel.
And critically, oxidizer for rocket fuel to get future missions back home. ISRU is key for sustainable human presence.
And scientifically, Perseverance has a laser focus compared to Curiosity.
Yeah, it builds directly on Curiosity's findings. Curiosity looked for past habitability. Did Mars have the right conditions for life? Perseverance is looking for direct evidence of ancient microbial life, actual biosignatures.
How? What tools does it have?
It's got advanced instruments. RIMAFAX is the first ground-penetrating radar on a rover, lets it map geologic layers underground, maybe find buried ice or brine layers down to 10 meters or so.
Wow.
And then PXL and Sherlock, they use X-rays and UV lasers to analyze rock chemistry and look for organic molecules at a microscopic scale. Really fine detail.
Before we get to the samples it's collecting, we should definitely mention the international side. China's Zhurong rover landed successfully in 2021 too, right?
Absolutely. A huge achievement for CNSA, landing an orbiter, lander, and rover successfully on their very first independent Mars mission. Zhurong explored Utopia Planitia, solar-powered, also carried ground-penetrating radar.
And ESA's rover is still upcoming.
Right, the ExoMars Rosalind Franklin rover. Its mission is focused on deep drilling down to 2 meters, specifically looking for organic molecules shielded from surface radiation. It's faced delays, but it's a key part of the international effort.
It really is a global endeavor now. But the tech demo that absolutely stole the show recently, opening up a whole new dimension, literally the sky,
Right.
was Ingenuity, the helicopter.
Oh, Ingenuity. Just incredible. What a moment. Definitely the Kitty Hawk moment of another world.
First powered, controlled flight on another planet. How hard was that technically? That atmosphere is so thin.
Incredibly hard.
Yeah.
The Martian atmosphere is less than 1% the density of Earth's at sea level. So to get lift, Ingenuity, this tiny thing, about 2 kilograms,
So,
needed these specially designed, very light, very rigid carbon composite blades. And they had to spin incredibly fast, over 2,500 RPM, much faster than helicopters on Earth, all just to get enough lift for maybe 90 seconds of flight at a time.
90 seconds max flight. Wow. And despite all that cutting-edge engineering, what was one of the most surprising lessons learned from Ingenuity's mission? It lasted way longer than planned.
It did. Designed for 5 test flights, it flew 72 times.
Yeah.
But maybe the biggest hardware surprise was resilience. NASA had always been very cautious about radiation hardening, needing expensive custom chips.
Right.
Ingenuity used a lot of off-the-shelf components, commercial stuff, including processors you'd find in cell phones. And they held up surprisingly well against the cosmic rays and radiation environment.
That's huge.
Yeah, it suggests maybe we don't always need the most expensive, custom-hardened parts. Opens the door for using cheaper, more capable commercial processors in future missions, potentially.
And Ingenuity wasn't just flying, it became a real scout for Perseverance, didn't it? Despite facing challenges like dust, cold, navigation glitches.
Absolutely. The JPO team kept pushing its limits. They flew it higher, up to 24 meters, faster, up to 10 meters per second. It provided invaluable aerial scouting, spotting interesting geology, planning routes for Perseverance. Just fantastic synergy.
Until its final flight.
Until Flight 72, yeah. It suffered damage to its rotor blades during a landing, likely due to navigation issues over sandy terrain with few landmarks. But what a stunning success overall.
Okay, so Ingenuity showed us the air. Perseverance is back on the ground, securing arguably the ultimate prize. Samples from Mars, sample return, MSR. This sounds like the most complex robotic mission ever conceived. Why is bringing rocks back absolutely essential?
It's essential because, ultimately, the instruments we need to definitively search for signs of past life or precisely date the rocks are just too big, too complex, too power-hungry to send to Mars.
Or haven't even been invented yet.
Exactly. We need the full power of Earth-based laboratories. Perseverance is drilling core samples, sealing them in pristine titanium tubes. It's already cached, I think, 12 scientifically chosen samples, collected over 30 total so far. Ready for pickup.
And this pickup, it's not just one mission, is it? It's like a multi-stage relay race across space.
It really is a massive international effort between NASA and ESA. Step 1. A future sample retrieval lander arrives. It might carry its own small fetch rover to collect the tubes Perseverance leaves behind.
Okay.
Step 2. Those samples get loaded into the Mars Ascent Vehicle, the MAV.
Stop there. The MAV, that's the rocket that launches from Mars.
The first launch from another planet. Yes,
Yeah.
a monumental engineering challenge in itself.
Mind-boggling. Okay, so it launches the samples into Mars orbit. Then what?
Then step 3. The ESA developed Earth Return Orbiter, ERO rendezvous, the sample container in Mars orbit, and captures it. Then the ERO uses its own efficient solar electric propulsion to fly all the way back to Earth. As it approaches Earth, it performs the final step. Step 4. Releasing the Earth entry system containing the samples aiming it for a safe landing in a designated zone, probably somewhere like the Utah desert.
Wow. Lander, fetch rover, Mars rocket, orbiting catcher, interplanetary cruise ship, Earth reentry vehicle. The complexity is just staggering.
It truly is.
So, assuming all that works, what are the really big questions these samples could finally answer back here in our labs?
The Holy Grail is definitive evidence of ancient life, if it's there, preserved perhaps in those sedimentary rocks from Jezrero's ancient river delta. But just as importantly, maybe more fundamentally, we'll be able to use techniques here to get absolute radiometric dating on those rocks.
Pin down the timeline.
Exactly. Determine the precise ages of geologic units in Jezrero, create a rock-solid timeline for when water flowed, when the climate changed, when Mars became the cold, dry place it is today. That's fundamental planetary science.
Looking back at this whole journey, from Sojourner's first tentative wheel tracks to Perseverance caching samples for return, what strikes me is how each step built on the last. Failures weren't endpoints, they were lessons.
That's exactly it. Mars exploration wasn't conquered by one single mission, one brilliant idea. It yielded, slowly, painfully sometimes, to generations of engineers and scientists who learned, adapted, refined the technology, pushed the autonomy, and just kept trying. It's persistent, generational learning written across the red planet.
And the next answers likely come from rocks waiting in a little titanium tube. This is Curious Minds. Thank you for being on this trip with us. Stay curious, stay ground.